Top of the line.
Where? Which?
There's three. There's
Is
one.
it a lecture?
There's a
If
Costco
it
in
was
West
a lecture,
London.
then you could be like, okay.
I think. That's honestly, I didn't think initially that Costco was that good, but like kind of a Costco guy now. Because I saw it there one time, and I was like, I'm too late. Yeah, pretty much. Yeah, because I'm always treating that close. Actually, one of the course I ran my few guys. How have you been keeping up? Did you get your results from That's so stupid.
No, but I didn't like what
You see why I hate it?
No, I really like it actually.
You and Clarence both just enjoy your NLP stuff.
I think it's really fun. Like it's actually not as solid.
That's what I'm saying. That's why I hate it.
It's too far up, like.
Or you can be given the solution so it's impossible to achieve. Because so you learning to use versionary.
Well, yeah, it's like basically just like terms of consistent internal text. Different types of text. Like motion code, motion code. No. That's one I sent in.
A lot of that stuff's done.
Yeah, but it's just the thing is like, you have to find their own, like, production level methodology. It's just like,
How'd you get from this stuff?
I was doing like this, for learning
Because that one day a week, like 8 hours.
Okay, so welcome to this lecture 4. So this is our this is week 5 and skip one lecture. So this is lecture 4. So originally next week would be reading week, but we're really sorry that I have the replacement lecture. So next week at 12 it would be lecture 5, and then at 2 o'clock, so that will be the end of the lecture, and then 2 to 1, 2 to 3, that will be the replacement seminar, okay, for group 1 seminar. Okay, so I'll try to record all of these, including the seminar, so that if you originally planned that you would be away in the reading week, so you would at least have the recording. So you can access back to the Moodle to get the recording. So you haven't done, if you haven't done that, so this is where the recording, so if you click in it, so there will be a list of recordings, so make sure it will be clear for you where the next week recording for the lecture and seminar is, okay? So if you still don't know the time and venue, so please let me know. I think the school should officially have sent the venue and time in your email. So if you don't know that, so let me know. I'll actually put it on the announcement as well for the time and venue later on, okay? Now, let's get back to the exercise. So let's get back to what we have done in the last lecture, okay? So in the last lecture, I think I would revise on our last part a bit. Last part of last lecture, we were talking about estimators, right? So from the ARMA model, we changed to how to estimate these models, starting from the AR model. So for the ARP model, so we can actually use different techniques to estimate. So the first technique I introduced in the last part is actually the moment estimators. So people call it walk estimator. So when I talk about moment estimator for AR model, it's basically the walk estimator. So you set up the Walker equations, basically equating theoretical and empirical moment, population and empirical moment, and then you get your moment estimator, okay? And one of the important ingredients in the moment estimators is you need to know the formula for estimating the empirical moments, okay? So in the last lecture, we talked about the preferred estimator, right, for all the autocovariance sequence estimator. So the ACVS, so you use S to estimate, where the denominator will be 1t rather than t minus h. H is the lag, okay? So you use 1 minus t, 1 over t rather than 1 over t minus h because of various reasons that we've talked about in last lecture. One of the important reasons is if you use 1 over t, then the ACVS estimated will actually be a positive semi-definite, okay? If you use 1 over t minus h, then the positive semi-definite is lost in general, okay? So people would rather preserve this positive semi-definiteness in ACVS. At the same time, usually the mean square estimate, the mean square error is actually smaller, okay? So hopefully most of you have done this week exercise, so you should be able to see for yourself that indeed, at least for white noise, the preferred estimator for the ACVS is actually having smaller mean square error, okay? So I'll talk about that in the seminar, but let's go to the lecture for now. So if you can see clearly the board, let me know, okay? So my screen is blank here, so I cannot see if you are seeing this clearly enough. Or if something is not on focus, let me know, okay? So we will start with another kind of estimators, okay, for the ARMA model. So we talk about your walk estimator. This time we talk about least square estimator, okay? So least square estimator, rather than just for AR, so I can generalize it for the ARMA model. So this should be pretty complicated, right? Given that your ARMA model is something like this, so if you remember, it's a bunch of variables that is autoregressive in nature, so that's from the AR part. and then is the MA component. So that's the MAQ component. So they are added together to form an Armour equation. Where you have epsilon T is white noise with mean 0 and variance sigma squared. Okay, so what do you need to estimate here in this equation? So you need to estimate the parameters are, first of all, the alpha, of course, and also the AR and MA parameters. So let me summarize them as phi and theta. So both as a factor, okay? So where phi is actually defined as a column factor of all the phi 1 up to phi p. And then the theta is similar, so it's theta 1 up to theta q, right? So you have P, AR parameters, and then Q, MA parameters. So you need to estimate these, as well as sigma square, so we'll talk about that later. But let's estimate all these parameters first. Especially important is the phi and theta. So if we are doing least square estimation, so if we are doing least square estimation, so we would set our squared error function Q as the sum of the errors, right? That's how you do the least square estimation in linear model. So this is pretty much similar. So sum of the errors is sum of the epsilon t squared. And now epsilon t is your xt minus the bunch of XR, AR, and MA parts. P to minus epsilon t minus theta 1, epsilon t minus 1 minus up to theta q, epsilon t minus q squared. Okay, so that's the least square estimator. And what is your data? Your data is, let's say, observed x1 up to xt. So that's the only thing you observe, right? You observe the process x, capital T instances. That's your data. So what you cannot observe is, of course, the epsilon t and the parameters of interest. Okay. So here, how do you actually estimate this? Okay. So if you put t equals 1, what you have is, well, alpha plus phi 1 x0 plus phi 2 x minus 1 plus up to phi p x 1 minus p, and so on and so forth, which is certainly can exist in real world, but you didn't observe that, right? You didn't observe x0, x minus 1, x minus 2, etc. Okay? And certainly you don't observe all the epsilons. Okay? So what do you do here is actually to set something to be 0 first. So you initialize some condition first so that you can iterate the least square estimator. So let me write it down what you need to initialize first, okay? So you need to initialize epsilon p plus 1 minus k equals to 0 for all integer k larger than or equal to 1. So that is to say your epsilon p minus 1, back to epsilon 1, epsilon 0, epsilon minus 1, and so on and so forth. They're all 0. So why do why do you need that? Well, if you put t equals to 1, so you have epsilon 1. Look at the equation at the top. So you have epsilon 1 here, and then you have epsilon 0 all the way up to epsilon 1 minus q. Okay? And if you put t equals to p here, so you have epsilon p minus 1, epsilon p minus q, and so on and so forth. Okay? So all of these involve unknown epsilons, okay? And you don't know what their values are, okay? So starting from t equals to p plus 1, now if you put t equals to p plus 1 here, what happened is this portion is all observed, okay? So we have phi 1 x p and then phi 2 xp minus 1 up to phi p x1, okay? So all of these you can put data in. And then here you have epsilon p plus 1, okay? Plus theta 1 epsilon p and so on and so forth. So epsilon p plus 1 is fine, so this is put in here to be minimized, okay? But what about the string of the other earlier epsilons, okay? So these sort of string of earlier epsilons are those that we don't know. So we set them all to 0, okay? So that starting from t equals to p plus 1, we can express epsilon p plus 1 in terms of this error, okay? In terms of this string of error that you can calculate, okay? And then iteratively at p plus 2, so all the x, of course, are observed already. And then epsilon p plus 2, so this is to be expressed as the this subtraction here. So you have epsilon p plus 2 plus theta 1 epsilon p plus 1. And then all else are 0. But what is theta 1 epsilon t plus 1 p plus 1? Epsilon p plus 1 is actually expressed earlier as this kind of error, okay? So you have iteratively more and more complex function of phi and theta in terms of how do you calculate epsilons, okay? So let me give you two very concrete example for epsilon p plus 1. Then equals to what? xp plus 1 minus alpha minus phi 1 xp minus up to phi p x1. And that's it. So you can directly put this into this Q, okay? So epsilon p plus 1 square is this squared, okay? So it's a function of the parameters. But what is epsilon p plus 2? Now epsilon p plus 2 will equals to xp plus 2 minus alpha minus phi 1 x p plus 1 down to minus phi p x2, right? But there's something more, so it's plus theta 1 epsilon p plus 1. I'm just using the Armour equation to get this epsilon p plus 2. And then because we set everything else earlier to 0, so that's it, okay? So epsilon p plus 2 is a function of something that we expect, that you expect this here, right? And something you unexpect, so because there's theta 1 epsilon p plus 1, which also iteratively depends on the data as well as the parameters, okay? So as you can imagine, epsilon p plus 3 then becomes yet again more complicated, and so on and so forth, okay? So when you talk about minimizing Q here, which is sum of the epsilon t square, is actually a highly complicated function of the parameters phi and theta, and the data as well, of course. Okay. So yeah, but so I'm not going to talk into a lot of detail into how exactly this is minimized. Okay. So this is still tractable, but I'm not going to teach deeper than that. So other than, so you need to know, of course, our Alma equation. So least square estimation, how do you set up the function to be minimized? Okay. And then what initial value will facilitate the start of the epsilons, okay? So the first epsilon that you actually can be expressed in terms of the data and parameter, actually epsilon p plus 1, okay? If you set everything else earlier for the noise to be 0, okay? So, just a little bit more to say about the least square estimator. So this is done in R as well. So if you do the ARIMA estimator, so it usually will give you the estimator, which is maximum likelihood. Okay, so but maximum likelihood estimator is actually the least square estimator. So we'll later on see that. Okay, so in R, that is exactly what it does. So I assume all the early epsilons are 0, and then iteratively. So it will basically be able to form the sum of the epsilon t square in terms of the parameters. But you may ask, so, well, is it accurate? So we are, after all, setting all the early epsilons at 0, where obviously, of course, they will not be. Okay. So the underlying assumption underlying assumption is that, of course, your sample size is large. Usually you assume that your sample size is much larger than P plus Q. So your P phi parameters, AR parameters, and you have Q, MA parameters. Okay, so you usually assume T is much larger than this is where that's much larger than, okay. So practically, if P and Q are, say, 4 or 5, so P plus Q may be in the order of tens, then your T usually will be in the order of hundreds, okay, if not thousands. So that the assumption of early epsilons is 0, they are asymptotically negligible. So you will get more accurate estimators for phi and theta as t becomes larger and larger. So one last thing, so of course we can express, and you need to express your epsilon s for s larger than p. In terms of alpha, phi, and theta. And the data observed. So I've just shown you the first two, epsilon p plus 1, epsilon p plus 2. So it will progressively get more complicated as a function, but there you go. So I'll keep track of all these, and can give you the least square estimator back by minimizing this. But we will not talk about that. So detail of this algorithm will not be talked about. So we'll only talk about what you need to know is all presented here. So you need to know the setup of the least square estimator. So what are the initial values that you need to take? So and the reason for that, and how do you express your epsilon in terms of the original observed data and the observed parameters, okay? So that's all I'm going to ask you. Now, with this very general least square estimator, so let's look at the maximum likelihood estimator, okay? So this is something I need you to know as well. So I suppose all of you, if most of you, if not all, would have studied the maximum likelihood estimator. So, so what's different between this maximum likelihood estimator and the least square estimator? Well, so for all of you, so there's a recap here, of course. So the data, of course, is x1 up to xt. So sample size is capital T here. And your equation, well, the same. Of course, it's the same, but there's a one tiny bit difference here at the end. So after theta q, epsilon t minus q, so you write your epsilon t, right? So this time, for maximum likelihood estimator, of course, you need to know the distribution. Okay, conditional distribution, marginal distribution, whatever, for the noise. Okay, so this time we're assuming the epsilon t's are RID, normal with mean zero and variance sigma squared. Okay, so that's your assumption for the MLE to be able to be calculated. Again, with the same initial condition. So initial condition is epsilon p plus 1 minus k equals to 0 for k larger than 1. So this reverse A is for all, okay? So I should write English. Okay, so xt. So with this knowledge, so you can actually write down the conditional distribution like this for xt. So xt, given that you know all the previous values of the x, actually follows a normal distribution plus plus all the previous values of x, of course, p minus p, and then plus the epsilons as well. Okay, so you are basically assuming that you know the information up to time t. So given the previous values of the x's, okay, so and with this initial condition, so remember in the previous page when we talk about the least square estimator, okay, so we start with what, the epsilon p plus 1, right, being expressed as a function of the data, as well as the parameters. So here is the same thing. Okay, so if you put x1 in, x1, well, you don't know, but xt, for t being larger than actually, it has to be larger than or equal to p plus 1, actually, in order to start to be able to express as something you know. So xp plus 1 will be what? Given all the past x there, so it'll be alpha plus phi 1 xp up to phi p x1. And that's it. So all the epsilons will be 0. Okay? And so on and so forth. All right? So all these past epsilons actually can be expressed iteratively as function of data as well as the parameters. Okay? So again, this similarly linear model for the x and epsilons, for the phi and theta, is actually, in the end, will be iteratively a complicated function for phi and theta, okay? At least a high degree polynomial for phi and theta. But we know that, okay? So we know this, with this initial condition, so we know iteratively the conditional distribution for xt. So what to do with that? Well, the maximum likelihood estimator talk about the likelihood function. So what is a likelihood function? So the simplest is to say that likelihood function is the probability or density that you get what you observe. Okay, so it's basically here for continuous distribution. This is a density for your data that you observe. Okay, so this basically can be written as the joint density for the data you observe, x1 up to xt. So here F is the joint density. And this joint density can actually be expressed as a product of conditional density multiplied with marginal density. Here you can see that the conditional density is x for x capital T given any past values. So originally it's a joint density for x1 up to x capital T, and it can be expressed as the conditional density for x capital T only, given all the past values of x, multiplied with the marginal, the joint density for x1 up to xt minus 1. Okay? So this is just a simple formula for conditional density. Okay? And then what? And then we can actually iterate this. So this equals to we iterate this, so we continue this process expressing the marginal density, the joint density for x1 up to xt minus 1. Express this as a conditional density of xt minus 1 given xt minus 2 and so on back to x1. And then multiply the joint density for x1 up to xt minus 2. So what we are saying is this joint density x1 up to x capital T can actually be expressed as different conditional density for xj given x1 up to xj minus 1. So for j equals 2 to t. So if we iterate the process, so it will be down to, so conditional density of x2 given x1, and then you need to multiply the, finally, the marginal density of x1. And that's it, Okay, so that's all we can do because we only observed down to x1, right? We didn't observe x0 and anything before that. Okay. So, and why do we do this? Well, I've just explained that you know the conditional distribution of xt given all the past variables, right? So this is exactly it. Because you know the conditional distribution are all normal, so you know the density of these. Or the fxj given x1 up to xj minus 1, so you know that they are normal density. And you can write them out, okay? So each one of them, let me write it out for you. So each one of them equals to, so if you don't remember, so it's 1 over sigma, square root of 2 pi. Then it's the exponentiation of the conditional mean. So it's xj minus the conditional mean, so it's a long string of things. Right? Silent, so that shouldn't be plus, sorry. That should be continue to subtract theta 1, sin j minus 1, and so on and so forth, up to theta q, epsilon j minus q. Sorry about that. So it's xj minus the string here, basically. So xj minus the conditional mean squared divided by 2 sigma squared, right? So that's your density. So each fj, xj given x1 up to xj minus 1, so it can be expressed like this. So you know almost all of them. I say almost because you don't know fx1. What's the marginal density of x1? So who knows? And who cares? With t going to infinity. So if your sample size is really small, then maybe you need to care about these assumptions. But with only medium sample size, so usually this assumption on x1 can be dropped. Okay, so people don't care about the fx1 anymore, and they only maximize the conditional density. The conditional density, which is the product xj from 2 to t, f of xj given x1 up to xj minus 1. So in R, when you talk about maximum likelihood estimators, then the whole process is like this, okay? So you don't actually maximize the exact likelihood, but the conditional likelihood, dropping the first term fx1 here. And with these, then you should be able to see that so with this setup, you should be able to immediately see that under normality assumption, under RID normal errors, the maximum likelihood estimator for alpha, phi, and theta will be the same as the least square estimator. So this is under RID normal errors. And why is that? Well, you're taking product of this exponential density, the normal density. So product of this exponential is basically exponential of the sum, right? So exponential to the minus of the sum of these squares is exactly the sum of the epsilon t squared. And you maximize this likelihood basically means to minimize the sum of the epsilon squareds in this MLE. So maximizing the maximum likelihood is the same as maximizing the likelihood is here indeed the same as minimizing the sum of squares of epsilons. So under normality, so MLE and least square estimator is the same, okay? So I think you should have studied some of these conclusions in linear model, but for time series estimator under certain initial conditions, so they are the same, okay? So the same conclusion applies. MLE is the same as least square estimator under normality assumption, okay? So that's, in one sentence, encapsulate all these. So you need to know what the maximum likelihood estimator entail, what is the conditional density. So this is the conditional density. How do we express it from the joint density to a product of conditional densities? And what is the formula for the density itself, for the conditional density? Okay, so you need to know all this. And any questions? Yeah.
Actually, under the independence assumption, that's why we can write it out as like these products. Otherwise, if we didn't have independence, it wouldn't.
Good questions. This product can always be written.
Always written. Okay.
Can always be written like this. You see, this is conditional density multiplied by the marginal, the joint density. So this is just the formula for conditional density, okay? So no matter the xt's are correlated or not, this formula for conditional density holds. So it can always be written as a product. The use of these IID errors comes in writing down the formula for these conditional densities themselves, okay? Yeah. Very good. Okay, so with this knowledge, perhaps we can talk about some asymptotics, but before that, so let me go through one more. So I know there is a little bit of. So I promise this will be the last slide. Talk about these least square estimators, okay? But there's one more, okay? Because it's a little bit special when we talk about AR model. So least square estimator. So I've talked about the general schematic approach to solving the least square estimator problem for very general ARMA model. So why do I revisit this for AR model? Because we can talk a little bit more in this scenario, just like the walk estimator, okay? So let's look at it very quickly. So if your data, again, is x1 up to x capital T, then your ARP model is the constant alpha plus phi 1 xt minus 1. So up to now, you should be able to write down the ARMA model very quickly, even in terms of the backshift operator. Okay. So your epsilon t again will be generally a white noise. So how do we directly estimate the phase? In AR model, so you can actually write this xp plus 1 equals to alpha plus phi 1 xp plus up to phi px1 plus epsilon p plus 1, and then xp plus 2 equals to alpha plus phi 1 xp plus 1 plus up to phi p x2, and then plus epsilon p plus 2 down to x capital T equals to alpha plus phi 1 x t minus 1 plus up to phi p x t minus p plus epsilon capital T. Okay, so that's all your data. You cannot write xp because it will go down to x0 where you don't have data. Okay, so therefore you start with xp plus 1 up to x capital T. That's the first nuance that you need to note. Then what else? Well, this is a system of linear equations, right? Just like the U-Walker equations. But this is a little bit different. This directly involves the data themselves. You can actually write this as a system in terms of vectors and matrices. So you can define this as the response factor on the left. So this you can define it as, let's say, y. And then on the right hand side, well, it will be, first of all, you have an intercept term. So intercept term in a linear model, this is basically a linear model setup, right? So for a linear model with intercept term, so you have columns of ones, and then it will be the data themselves, xp down to x1, and then xp plus 1 down to x2. Right, it all copies from here. So this is xp down to x1, this xp plus 1 down to x2 in the second row, and so on and so forth. Down to the last row, which is xt minus 1 down to xt minus p. So this is xt minus 1 and xt minus p. And it is the whole thing multiplied with alpha, phi 1, phi 2, all the way up to phi p. So try to verify that this represents the f-valve. Of course, you need to add the epsilons. Epsilon t. Yeah. So try to verify that this system represents this system. Okay, the two systems are the same. So this one you can maybe define this as a matrix X. Of course, it depends on the data X, and also there's a columns of ones because of the intercept term alpha. This you can define as, let's say, beta, and this you can define it as a vector epsilon. So if you write this in terms of vector and matrix form for the model, so this is y equals to x beta plus epsilon, and least square estimator, least square problem will be to find beta that minimize y minus x beta all squared, right? And what's the solution to this problem, to this general problem? Minimizing y minus x beta square norm with respect to beta. Well, the least square estimator for beta hat will then be x transpose x inverse x transpose y. Okay. So this is another more explicit least square estimator when your model is actually in an explicit form ARP model. And as your sample size gets larger, your least square estimator is a consistent estimator. For the true parameter beta, okay? And so thus, for the least square estimator we talk about for ARMA model, as well as the maximum likelihood estimator. So asymptotically, as t becomes large, they are all asymptotically equivalent. But of course, t is always finite, so sample size is always finite. There's no infinite sample size. So if t is smaller, more trustworthy estimator actually will be the maximum likelihood estimator, as well as the previous least square estimator. This sometimes people call the forward least square, this least square here. And when sample size is small, they may not be trustworthy enough, but as sample size gets larger, they are all asymptotically equivalent. Okay. So let me talk about some asymptotic results before we go to lecture notes to see some graphics. Okay, so least square estimator, maximum likelihood estimator. So I maybe start to get a little bit dry. But let's finish this with the asymptotics first. So there's some asymptotic results that I want you to know. So remember, we talked about your Walker estimator, so that's some time ago from last lecture. So take this as a recap. So your Walker estimator for an ARP model, your phi head is what? Your phi head is a big matrix inverse multiplied with a factor, right? Where your big matrix is actually a matrix of the ACVS. And your factor gamma P will be starting from S1 all the way up to SP. So this is the result of solving the Walker equations. So remember what the Walker equations are. They're basically the system of equation that equating the ACVS, population ACVS with the empirical moment, basically. Okay, and what is the hat here? The hat is our preferred estimator, remember? 1 over t sum t from 1 to t minus h, xt plus h minus x bar, and then xt minus x bar. Right? So h runs from, it can be from 0, 1, anything. So -1, ±2, anything. So I'm just reminding you what the walk estimators are. So what are the asymptotic results? Well, the first asymptotic result is, so your walk estimator, of course, is consistent, and in fact, you know the asymptotic distribution. So it will be a factor of 0, and covariance matrix, in fact, in the end, depends on gamma p, okay? And this is convergence in distribution. So, by the way, so I talk about consistent estimator and then convergence in distribution. So consistent estimator being convergence in probability, okay? So beta hat is going to the true beta in probability. And here, the convergence in distribution, of course, is a little bit weaker than convergence to probability. Convergence to probability is a little bit stronger statement, okay? If you don't know what convergence in different form, okay, convergence in mean square, convergence in distribution, convergence in probability, just to check out your undergraduate statistics textbook, okay? So I will not actually explicitly test this. In fact, you probably don't need this particular knowledge to differentiate between this mode of convergence, but you should know, okay? Actually, you should know. So the other asymptotic result is the sigma square hat from the you walk estimator has this asymptotic distribution, okay? So that's it. So if I ask about asymptotic result, that's basically in a black box. I haven't proved it, right? I didn't ask for a proof, but somehow I want you to know this is exactly these two, okay? And that's it. Or others, maybe I'll ask you to prove, etc., etc. Okay, but these two is certainly out of the scope of this course to prove it. But if you truly want to know how to prove this, so this is in Brockwell and Davis, the people call this Bible for time series analysis. So let me give you one very quick example. So if you are AR1 model, your gamma 1, so it's a 1 by 1 matrix, is just a scalar, S0. And remember, S0 for an AR1 is what? Sigma squared divided by 1 minus phi squared. So at this stage, hopefully, you remember all these formulas. Okay, this is easier. Okay. Certainly not required, and usually I'll ask you to prove these results first, very quickly. But here, what I want to demonstrate is if you use this asymptotic result, so phi hat will be asymptotically normal with variance sigma squared times gamma p inverse, which is S0 inverse, which is 1 minus phi squared divided by sigma squared, which is normal with mean 0 and variance equals to 1 minus phi squared. So, well, what's the use of this? So practically, so as you should see from many undergraduate statistics textbook or practice, so we'll use T phi hat minus phi will be similar to a normal distribution with mean 0 and variance 1 minus phi hat square. Because of this asymptotic result, so it implies that root t times 1 minus phi times phi hat minus phi, and then divided by the square root of 1 minus phi hat squared will be approximately a pivot, so the standard normal. So we can use this result to do an inference for phi hat, okay, for phi. So you can construct confidence interval for phi, do testing, etc., etc. Okay. So if you want to construct confidence interval, using this result, it will be phi hat plus or minus 1.96 times 1 minus phi hat square divided by t, right? This will be an approximate 95% confidence interval for phi, right? So this 1 minus phi hat square divided by t comes from this term here. So root t divided by 1 minus phi hat square multiplied on the right hand side to 1.96, that will be 1.96 times square root of 1 minus phi hat square divided by t. Okay, so let's come back at 2:10, and then we'll continue with these results.
No, that's great to know because we barely started and I forgot about it.
Yeah. So what you guys are doing is complicated. What you guys are doing is there's the world.
But you're doing like the crop thing, right? Or do you think it's too complicated?
It was like, I don't know, like we really didn't think this through at all.
Why?
Because it's like, to predict crop
Mhm.
not future cells. So we're like changing the prediction test, and we're assuming that
Yeah.
all the variables are just great predictors of our targets, which is
Is
like
there no
not
other
true.
data set that
Yeah.
on like how to predict like that puts future prices and crop yield into perspective?
That's a good question. As good a data set.
Mhm.
You would use, sure, like the data set we're using is just it's massive. It's just like it's limitless. It's like region data daily for
In the entire world.
practically, yeah.
Crazy.
For like here's like that's like satellite images
Mhm.
of like the entire
Okay, so let's continue. So we were talking about asymptotics for the U-Walker estimator, okay? And we have demonstrated this in the AR1 model. Now there are several other important asymptotics for the estimators. So one of which is something that it is actually displayed on your ACF plot, which I'm going to demonstrate. So if you have an MA model, in particular with order Q, so your epsilon t is actually following IID mean zero and variance sigma square. So I don't set fixed distribution for this. So you can see that it's IID, not IID normal. So it's only IID with mean zero and variance sigma square, okay? And the fourth order moment is finite, okay? So if this is the case, then you have another important asymptotic result. Now this one is what we always use actually. So let me write it down in its full form first. So straight from 1 to Q, rho J squared, okay? In fact, this is what in the lecture note said, so let me write K minus 1 instead of Q, okay? K larger than Q. And what is rho K? Well, this is equals to, remember, the SK hat divided by S naught hat, right? So what's important in this estimator? Well, first of all, if Q equals to 0, that is, the data is a white noise. So the data follows a white noise, right? Then the above results imply what? Implied root T times rho K hat is going to normal with mean 0. Well, if Q is 0, so as long as K is larger than 0, so for any K, right? And all the rho J will be actually 0 for white noise, so this is 0. So 1 plus 2 times 0, this is 1. So just standard normal. For any K larger than 0. So if your original data is a white noise, you form all the rho K hats, so you calculate all the rho K hats. So these are estimators. Asymptotically, they will follow a standard normal distribution after adjusting for root T. So what does it imply? Well, it implies that if at any K, at any K larger than 1, so you can test. So you can use the above result. To test if the data indeed is a white noise. So if your data is a white noise, then let me write Wn as white noise. So if data is white noise, then this result is should approximately hold. So rho k hat should be, so this is approximately distributed as normal with mean 0 and variance is 1 over t, right? So
So we'd observe our data and then see if it follows this distribution, and if it does, then we can say, oh, it's probably gonna be a white noise.
yes,
Okay.
you can form a, you can actually, so rho k hat divided by one over square root of t and so I want to write it a little bit more. The original probability statement, okay, so basically it means this is approximately, if I do 1.96, that's 97.5%. So it should be 1 point, yeah. Anyway.
Why is the rho k distributed with a 1 divided by t variance?
This one?
Yes, yes.
Oh, we use this. We use this asymptotic result. So asymptotically, when t is large, then rho k hat is multiplied by root t will be approximately standard normal.
Mm-hmm.
So we basically divided both sides by square root of t.
T, yeah.
And 1 over root t times normal, so the variance will be 1 over t. So it's like, so it's like the variance of a times x is a squared times variance of x, right? Sorry.
Thank you.
So there's always an a squared, okay? So the variance will be, now the a is 1 over root t, so a squared will be 1 over t. So basically, we use plus or minus 1.96 divided by root t. And see if this band contains your rho k hat, okay? So you can do this test in one go for many k by just looking at the ACF, right? So let's look back at the PC very quickly. So this is generating an ARIMA model again. So this is an ARMA model. Okay. Well, let's generate some white noise, okay? So if I want to generate white noise, so this, the quickest way will be okay. And then you can plot your ACF for y. So the upper graph is the ACF, okay? So at any lag, the distribution for roll K-hat should approximately hold, okay? And this blue dotted line is exactly plus or minus 1.96 divided by square root of t. Now t is 300. So you can see this blue dotted line is around here, at 1.1 and minus 0.1. And you can see that most of the states are actually, as the distribution predicted, most of them will fall below, within the blue dotted line. Okay, only approximately, actually only approximately 2.5% actually, not 5%, will be within, will be outside the state, will be outside this blue dotted band. Okay, so you can see that at lag 5, there's 1 sticking outside. In practice, usually, if you see 1 or 2 that is outside, that is fine. Okay, if your sample size is large, then usually doesn't depend on sample size. The sample size actually is adjusted in this blue dotted line. Okay, so usually if you see 1 or 2 that is outside, when you for the first maybe 30 to 50 lags, then it usually means okay, it looks really like a white noise. Okay, so this one, there's only 1 lag outside the blue dotted line, so it certainly looks like a white noise to me. Okay, the same for the PACF, but I haven't talked about the PACF yet for the asymptotic result. I will in a minute. Okay, now as opposed to if you look at X. So if you generate X, so this is ARMA 1.1 model, right? With phi equals to 0.5, theta equals to 1. So this is our ARMA 1.1 model. So you really won't expect this as look like a white noise. Indeed, if you plot the ACF graph for X, so you can see here, certainly first few lags consistently is placed outside the blue dotted band, which is again plus or minus 1.96 divided by square root of 300. Okay. So looking at every one of these lags, so you will reject the null hypothesis that this is a white noise, right? Because it's sticking outside the blue dotted band. Okay. And by looking at this ACF graph, you're basically looking at a lot of these tests simultaneously, right? You're looking at a lot of these testing white noise simultaneously. So that's the purpose of this blue dotted band. All right? It stems from this asymptotic result for roll head, when you have a white noise for your data. So that's the one that is more important because it's related to the display in R, which I've shown you in earlier lectures. Now, how about the PACF? PACF only have one result, and that's actually very simple. Let me go back to the .com here. So let me start with a new page. Okay. So for the PACF, that is one related result is actually the phi hat. Sorry, I should place it here. Okay. And that is related to AR model, okay? So one more general, but you remember, so for the ACF, I talk about MA model and then is asymptotic distribution when the data is actually following on white noise. Okay, so that's for ACF because ACF has cutoff, natural cutoff for MA model. And as for PACF, has a natural cutoff for AR model. So when we talk about PACF, we look at it through AR model, basically. So if we estimate this ARP model using an ARH model, here the H is the lag, with the lag H larger than P. For instance, if your real data is actually following AR1 model and you actually use an AR2 model to estimate it, so you overestimate the number of lags, right? Then that lag, which should be 0 in reality, right? So this estimator for lag, so which is also U-Walker estimator, by the way, okay? This is the U-Walker estimator. So guess what this distribution is? Well, it's a standard normal again. So if you have an AR2 model, you use an AR4 to estimate, so what is a 5.3 head and 5.4 head? So they all marginally will be looking like a standard normal after adjusting for root T. Okay, so important thing is H has to be larger than the true order P. Okay, so that one is related to PACF. Okay, so your PACF, remember, for an ARP model, your PACF is pi p, right? We use pi to denote PACF. And for an ARP model, pi p is exactly phi p. I think I have, I don't know if I've sent you some exercise to do that, but let me write it down here. For an ARP, the PACF at lag p is the AR coefficient, phi p. So I hope I have sent you some exercise to prove it this week or next week, okay? And it's because of this, so we have this asymptotic result related. So for lag P, okay, so it should be looking like phi P. So it certainly will not be standard normal when you calculate it is U-Walker estimator. But any further, so any lag H that is further than P, well, in reality they should be 0, right? The estimator, U-Walker estimator, should look like a standard normal after adjusting for root T. So the same blue dotted band applies, basically. So plus or minus 1.96 divided by root T band can be used as a test. For an ARP model. If you're looking at a lag H that is larger than P, okay? So complicated. So let's look at the computer. Okay, so what I mean is very simple actually in reality. So let's look back at, let's generate AR model instead. So let's remove this MA component. So this is okay, so we generate an AR model. So again, the sample size is 300, AR1 coefficient equals to 0.5 there. So if you look at the ACF2 of x, what happens? First of all, the ACF graph. The ACF graph is basically for you to look at if it looks like an MA model or actually a white noise, right? Basically a white noise. So does it look like a white noise? Well, it doesn't. Okay, so first, second, third, it's consistently sticking out of the plus minus 1.96 divided by root t. Okay, so doesn't look like a white noise. But how about an AR model? Does it look like an AR model, and what lag it is? Well, look at any lag. Well, they fall within the blue dotted line, 1.96 divided by root t. Okay, so using our knowledge of the asymptotic results, so all the phi hat, all the Euroca estimated phi hat should be approximately standard normal. Okay, with asymptotic variance equals to 1 over t. So they all, if it looks really like an AR1 model, for instance, so for any lag 2 onwards, all the PACF should be within this blue dotted band, okay? With a few exceptions, of course, because of the, this is only a 97.5% band, okay? But there's no exception actually, so all of them actually fall within the band. So it looks really like an AR1 model. So for the lag 1, it sticks out, okay? In fact, it sticks out truly like 0.5. So remember, we generate this as an AR1 model with phi 1 equals to 0.5. So the lag 1 PACF should look exactly like 0.5. Okay, and this is really close to 0.5. And then nothing else. So all the phi hat larger than 1 in lag, they are theoretically 0. And the distribution for the phi hat themselves, they are asymptotically standard normal after adjusting for root t. Okay. So all of them should be small enough to be covered within this blue dotted band, except for a few of them, okay, in reality. So here we're lucky, so all of them indeed fall within the blue dotted band. Okay. So ultimately, I'm basically introducing you again what the ACF graph and the PACF graph truly are and their purpose. The purpose is to identify if they look like a white noise or they look like an AR model. Okay, so here you can also test if it looks like an MA model. Okay, so if it's an MA model, it looks like maybe it's MA3. In all practical terms, perhaps an MA3 fits really well for this AR1 model as well. Sample size, remember, is only 300. Okay, so if you put a really complicated MA model, that surely will fit well for this AR1 as well. Remember, AR1 can be expressed at an MA infinity. Okay.
But it could be an MA3 model as well. Because
from this result, yeah. So you look at this, the third one still stick out, but then after that they're all
and could we
practically
describe
zero.
it with like an ARMA model?
Yeah.
1.3 as well.
Not 1.3, but just MA3. Okay. So if you look at this, it looks like an MA model. Okay. So, and the first 3 legs stick out, and then after that, they're all practically zero. So it's MA3.
But the first one uses MA3 and the second one gives us AR1.
Yeah.
So could we combine that to be an ARMA?
Don't combine them. You choose either one.
Okay.
Okay. Not combine. Combine is completely different.
Mm-hmm.
Yeah. So either one is fine. It's either your data shows you that you can either be an MA3 or it looks like an AR1.
Okay. And how would I recognize an ARMA model?
ARMA model will look more complicated. So if you see all these ACF or PACF, so have a lot of things sticks out consistently. Let me generate one for you. So the original one, so this is an ARMA 11, right? So what does the ACF2 look like? Now for this ARMA 11, so does it look like MA model? Okay, maybe MA2, but then you can see that there's some stakes consistently outside electricity. PACF, well, they're consistently outside for the first 10 lakhs, maybe for the first 10 lakhs, and then there's still something out there. So it's so complicated. When you combine, usually ARMA model will be like this, okay? So it doesn't mean the order for the MA or AR necessarily has to be large, but when they combine together, their ACF or PACF, it suddenly becomes complicated.
So there's no way for us to recognize this anymore?
There is, I just don't want to teach that particular complicated thing for you,
Okay.
because usually what do people do? Well, so the first two lengths, right, they're large, and then for PACF, so it looks like maybe after 8 legs, okay, so most of them are quite small in the end. So you usually try P and Q both of small values, so maybe Q equals to 2 here, or maybe P equals to, you can try 1 first, okay, and then try to look at the feet, okay. And what I'm talking about the fit is something I will talk about, okay. So basically model selection, okay. So you look at this Akagi information criterion. So I will explain what AIC is, okay, in a minute. So the purpose for ACF and PACF, okay, so mainly is for you to look at it. Does it look like MA or does it look like AR model? Here, both look complicated enough, so perhaps an ARMA model. Okay. So that's the real purpose for looking at ACF and PACF first, okay, for your data.
Is it common for you to be able to easily tell which one it is, or do they typically look very mixed?
Sometimes, most of the time, if you fit an AR model with large enough order, then they usually fit. They even usually overfit the data.
Okay.
Yeah. So just one with a large enough order is enough. Remember, they can be expressed in MA infinity. Yeah. MA infinity means practically after a certain length, practically 0. That's not important. Yeah. Okay. So, yeah. So here you may try to fit an MA 20, so no one will do that. So usually we'll try ARMA model instead. Okay. Very good. Very good. So let me quickly introduce 2 concepts now. So your next natural question is it's only for MA, AR or ARMA model. Let me go back to. So in the world of time series, of course, you got way more complicated time series than ARMA model, right? So you got way more complicated time series than ARMA models. So why do we obsess with ARMA models apart from they're easy? Well, this is not the answer, but partial answer. So there's something called void decomposition. So what is this? Well, suppose xt is a stationary time series. So weakly stationary, that's enough. Then the void decomposition tells us that we can actually express your xt equals to a certain time trend dt actually plus an ma infinity, okay? And this time trend, of course, is not just time dependent. They can be random, but random in the sense that is deterministic. Random at the same time deterministic. What do I even mean? Remember, deterministic here has a special meaning, okay? Deterministic here means given information up to t minus 1, dt is determined, okay? So in your exercise, you have done that already. So given, I remember there's an exercise, a sine and cosine curve, right? It's kind of random sine and cosine curve, but given xt minus 1 and xt minus 2, you know exactly the value of xt. Then xt is deterministic. It's still random, but is deterministic. Because given information up to t minus 1, you can determine exactly the value of it. That's called deterministic, okay? So any stationary time series can actually be decomposed as a deterministic time series plus an ma infinity, okay? So I haven't defined ft. Ft is information up to time t. And what is this epsilon? So apart from being an ma infinity, epsilon t is uncorrelated. With your deterministic trend dt. And of course, it's a white noise, okay? So any stationary time series almost look like an ma infinity. Apart from some deterministic time series that you need to extract out of it first. And this observation prompts people, first of all, to study armor process, okay? You remember all armor process, if it's stationary, they can be expressed as ma infinity, right? We have done that in the last 2 lectures. Well, if we can somehow transform our xt to kind of eliminate the deterministic time series, perhaps it looks like a deterministic trend or something of more known form, maybe quadratic trend, maybe some linear trend in housing prices, okay? So perhaps if we can transform our xt so that we can eliminate this dt altogether, what you're left with is just transformation, linear transformation of this ma infinity. Linear transformation of ma infinity is still ma infinity. So you can then use your knowledge of armor process to actually make inference or make estimation of the armor process in question. Okay, so the void decomposition is something that gives the credence to what I've actually taught being actually important, okay? They're not useless because all stationary time series can be expressed like this, okay? So find a good transformation And then in the end, what you're left with can be modeled using an ARMA process, ARMA, whatever. Okay. So that's the void decomposition. And before I talk about model selection, so let me see if I should talk about. Let me talk about decomposition then. So that's the natural. So the next natural topic is then the decomposition of time series, right? So we so want to transform it to remove that deterministic trend. And in practice, so if your time series look like there is a time trend, so this is not only deterministic, it's a constant. It's a constant dependent on t, okay, so it's a function of t. And then plus certain thing that is seasonal. So this is seasonal. That means CT is perhaps very similar to the T minus S, where S is something called the seasonality. We'll tackle that in next lecture. And then plus, finally, YT, so time trend mu T plus seasonal trend CT plus YT, which we call the microscopic part. So in the void decomposition, remember, this is similar to MMA infinity, okay? So we use our knowledge in our model to try to estimate YT, try to do prediction on YT, etc. But how do we estimate mu T and CT? Well, we don't estimate them, we try to eliminate them. That's the usual practice, okay? So we do one of the two things. So first thing is to transform xt to eliminate mu T and CT. Or you can do to estimate mu T and CT. So two things. So you can do one of the two. So let's talk about elimination first for the next 5 minutes before we end today's lecture. So if we want to eliminate trend and seasonality, so I've talked about this basically in the past. So we talk about the difference operator, right? Difference operator is just 1 minus the backshift operator. So first order difference of xt is just xt minus 1. And then second order difference is what? Well, let's calculate it. Second order difference is 1 minus b squared, which is 1 minus 2b plus b squared. Therefore, second order difference is xt minus 2xt minus 1 plus xt minus 2. That's second order difference. So first order difference, second order difference, whatever. And why they're important? Because a polynomial trend of degree d can be eliminated by delta to the power d. So a linear trend in time t can be removed when we take first order difference. So up to a constant, okay. It will not be exactly 0, but it will be equals to a constant, right? So a time trend minus the time trend previously, it will remove the term t. And what you're left with is just some constant, okay? And second order difference, well, you can use the second order difference. It can remove a quadratic trend, okay? So if mu t is t squared, for example, then this is t squared minus 2 t minus 1 squared plus t minus 2 squared. So everything will be removed, okay? So in the end is 2. So verify this, okay? So what you're left with is just constant. How about seasonality? Well, you have seasonal difference. We use this delta sub s to denote the seasonal difference. In terms of the back shift operator, it is 1 minus b to the power s. So delta s of xt is xt minus s. So if somehow you have a seasonal component, ct equals to ct minus s, then what is the seasonal difference of ct? This is ct minus s, it is 0, right? So we'll remove any seasonal component in your time series. So removing trend, removing seasonal component. So hopefully what you're left with is the microscopic part that is promised in the void decomposition, right? That is the part that hopefully we can use ARMA model to try to model it correctly. All right? So that's the whole premise of this time series analysis using ARMA model. All right? Just one more thing to note before we end the lecture. Okay. So delta d minus 1 and delta s of t squared will be equals to 2s. Okay. This should be delta. Okay, so let's just put delta first. Delta s t squared will be equals to 2s. So what I mean is, if there is a seasonal difference, the order of the difference operator can be one less, okay? So for t square, originally you have to be delta square, right? Now if you have applied seasonal difference already, so you only apply one more difference, that's delta, then what you're left with is still a constant, okay? So that's what I mean, okay? For a dth degree polynomial, if you have a seasonal difference already, so you only need delta to the d minus 1 rather than delta to the t, to the d. So in order to live with just a constant, okay? So that's all you need to know for this lecture. And I'll see you in next week's lecture, which is at 12 p.m. So for the venue and time, I will upload to the announcement for the ST418 page as well, okay? Yep. Yeah. Oh, you can take Thursday or yeah.
Okay.
Yeah. Thank you. I'll note your absence. Yeah.
You're going to have